This is a 7-minute video on what I'll call the causality conundrum in observational data. Observational data are data that are not generated by a controlled experiment. Now, economists are interested in causal effects. The book calls this the impact assessment question. I have a policy intervention I'm considering, and I want to know what its causal impact is on some outcome variable or variables that I care about. And this is a ceteris paribus concept, holding other things that might affect the outcome constant. I fully acknowledge there may be other determinants. A macro example of this question is in the Hall and Jones paper you'll read. They construct a variable called S, which is a measure of the quality of economic governance, and they hypothesize that S has a causal impact on the log of real GDP per worker, essentially on prosperity, holding other influences constant. A famous microexample is the paper by Miguel and Kremer in Econometrica 2004, one of the early randomized controlled trials. Their question was, if we treat children in northern Kenya for intestinal worms, will that increase their school attendance, and by how much? Acknowledging that there are other influences that could be at work as well. Well, to go back to the Hall and Jones example, the data in every case are going to give us correlations between the variables we measure. So here on the x-axis, I have the level of social infrastructure, country by country. Here on the y-axis, I have the log of real GDP per worker, and this is a pure cross-section of countries. You can see the two variables appear to be related. In fact, the sample correlation is 0.75, which is quite high. Now, regressions will capture this. If I asked you to fit an OLS regression through these data, you'd have a line that looks something like this, with a intercept here on the log y axis and with a slope of b. So if that's 1 unit there, the slope is b. And the estimate of b in these data is right here. It's the correlation. It's a scaled up version of the correlation coefficient. So regressions capture correlations, nothing more, nothing less. To extract evidence from that scatter plot or from the regression about causal effects, we need to impose some theoretical structure. And here I'm drawing on some terrific work by Judea Pearl and co-authors. So we're going to use the concept here of a path diagram, which is a diagram that relates a set of variables that may be observable or unobservable, and that uses arrows to denote all direct causal impacts the theory gives us between those variables. So here are 4 structural models, 4 different ones of the 2 variables we care about, and in each case I put in at least 2 other variables, the epsilons. In this case, these are unobserved random variables that encompass all of the unobserved determinants of these 2 variables. Very importantly, however, here in these theories, those 2 things are uncorrelated. They are not correlated with each other. Okay, so there are 4 theories, and I'm going to now show you data that are generated by these 4 theories. And we'll ask whether in those data the correlation that we see is evidence of causality from S to log of y. Just notice in these 4 models, in model 1 we look at that model and we see there is no causality directly between S and log y. In model 2, this one has a causal arrow from S to y, so in that model log y is causally impacted by S. Of course, it's also impacted by epsilon y. In model 3, the causality goes the other way, from log y to S. And in model 4, again, like in model 1, there's no direct causal link between S and log y at all, but both of them happen to be affected by a variable called W. So think of those 4 panels now. Here are simulations that I've put together in a fake cross-section of data. What I did was I specified the properties of the epsilons, and I drew those randomly, and I used the model to generate the causal links, and here is what I get. In the upper left-hand corner here is the case where the two variables are uncorrelated. You can see there's no definitive pattern relating them. By eye, you can pick up that they're uncorrelated. Here is S causing Y, and that gives you a sample correlation of 0.75. Here is Y causing S. That gives you a sample correlation of 0.75. And here is W causing both of them, and in that example, we have the same correlation. So correlation does not imply causation in observational data. I have three very different models here, only one of which has causation from S log Y. Well, unfortunately, the world is typically going to be even more complicated than this. Here's a model that combines all three of those patterns of causality that we saw, and this is the typical world we live in with observational data. I'm going to end by showing you one quite favorable situation we might be in, which is what if we could run an experiment in which we were the controllers of this thing, that we randomly assigned the values of S to countries with no reference to W, Z, or log Y. In other words, we were able to shut down the links from W, Z, and log Y so that the only thing left linking these two variables is a causal arrow S to Y. Well, in that world, in that experimental world, correlation between S and log Y in a big enough sample would give us the causal impact of S on log Y, even though there are three other variables here that also matter. Here are a few references, and we'll pick this up further in the seminar.